in our case, we know a priori that our kernel must be Hermitian. And this restricts the class where we can choose it. Okay?
These have we seen as functions from P and P cross P to 0.
Look at it from the intuitive point of view. What is this kernel? The kernel is why this is important. And if you remember the proof of the reconstruction theorem in the one-dimensional case, in the one-dimensional case, from this relation, we deduce omega n. But omega n is precisely the number that in one dimension defines a scalar product. What is the multidimensional analog? I have the scalar product in the n+1 space. So I have a vector Cn, I have an operator Aek daga, and I have A daga Ej, and I have another operator eta n. So this is the scalar product in the n+1 space. Taking a joint, I know that this is equal eta n A minus Ej A plus Ek Cn, but of course in the nth space. And this is what we call omega tilde. So omega tilde practically is the conditional scalar product on the n+1 space given the scalar product in the nth space. We can say, using the language of Hilbert module, that omega tilde n, this is an omega tilde n+1. I add 1 because I start from 0. Okay? So this is the restriction of omega tilde. Omega tilde is the full positive definite kernel. But then it is restricted to the Pn space. And this is the restriction on the Pn space. So let me write explicitly that Cn and eta n belong to Pn. So I get the restriction of the kernel to the n space. So in the language of Hilbert module, I can write that omega n uv is a minus u a daga, and this is a scalar product with values in the operator L A adjointable operators on P. When I don't put the n, it means that I consider operators on P. When I put the n, sorry, here I put n, so this is omega without n, okay? When I put the n, I have omega tilde n+1 uv is equal a so this is very important. It will be very important when we will discuss the induction construction. That will tell you the difference between a minus, a plus, and a plus, a minus. You see, because here, if I want to restrict this product, if I want to restrict this product to n, then I have to I start from n, so I restrict v on n, but a daga arrives in n+1, so here I will have a minus u n+1, because that is the domain. Okay, you will see why this will play a very important role in the reconstruction. So this is the idea. This kernel is simply in the language. In fact, there is also a note that we wrote with Michael Skyde to, in some sense, exploit this fact to formulate Hilbert interacting Fock space in the language of Hilbert modules. There is a small note if you are interested. I can send it to you. So these are the kernels that we are now that we have introduced, and okay. Now I wrote these commutation relations, so let us put some number because they will be important. So this we will call 1, 2, and now what we want to do, I will okay, maybe. Okay, now what I want to do is this. Remember that we have said that there are relations. I want to try to determine which are precisely these relations. Since the only new point with respect to the one-dimensional case are the type 2 commutation relation, it's clear that we have to study these commutators. You see, you understand what are the relations? Well, but let us study the commutators. So the first point is the lemma. Is the lemma that the commutation relations, we start from 2, are equivalent to the following constraint. The constraint is this, that omega 1, let me say in this notation, you see, the restriction of omega tilde on Pn. So omega tilde 1, so restricted to the first order orthogonal polynomial, is, we know it must be the necessary condition, symmetric, and is a real number. And this is a real number. But omega tilde n plus 1, omega tilde on higher order space will be a matrix, and what is crucial is that the imaginary part is equal to the imaginary, remember that by definition of omega tilde, this is, I want to write because it gives you insight. By definition of omega tilde, this is the imaginary part of A minus, what we wrote here, A minus J restricted n plus 1, A plus J, K restricted n. So this is just a definition. And the lemma tells you that this must be equal to the imaginary part of, there is an inversion of indices, A minus J plus the imaginary part, A0K, A0J. This is the relation. Now, you see, of course, here, well, I should put also the restrictions. but let me put here the restriction. This is restricted to n, and this is restricted to n. You see? So, now you understand why this relation is very important. This relation gives an information that took many years to arrive to understand this point. But look at this point. You see, on the left-hand side, I have combination minus plus. On the right-hand side, I have the combination plus minus. Now, why this is important? Because if you make explicit this product, you see, because the imaginary part is a linear operation, so it commutes with restriction. So this will become the imaginary part of a minus j, and we always start from n, but a minus brings you to n minus 1. So this will be a daga k restricted to n minus 1. And this here is gradation preserving, so no problem. Suggests you an induction, because suppose that I know that the imaginary part of the n plus 1 omega tilde kernel is obtained from the imaginary part of this product, which is not omega tilde, because omega tilde is minus plus. This is plus minus. But the imaginary part of this. Now look, this imaginary part involves only operator at the level n and minus 1. And here only at the level n. This operator requires the a daga, this operator requires a daga restricted on n minus 1. Essentially, what is the new point? This operator is algebraic. I know from the quantum decomposition. I didn't write the quantum decomposition, but I write. From the quantum decomposition, I know that for every j, xj is equal to a daga j plus a0j plus a minus j, and I rewrite this as a daga j equal xj minus a0j minus a minus j. But since this operator, since I have the full orthogonal gradation, which give me all the space, to say that this equality holds is exactly the same to say that this holds for the restrictions for each n. Two operators coincide if and only if they coincide on every subspace of the gradation. Okay? So now, this tells you that if I have, you see, a minus, what is a minus here? A minus is, if I want to have a minus in n, this is the adjoint of the creation operator, but in n minus 1. Because the creation increases by 1. So you see, from the point of view of induction, this suggests to you that if I know the creator at the n-1 level, and I give you an A0 at the n level, then I define a daga at the n level algebraic. See, it's clear the logic. This is the basic idea of the reconstruction theory. The problem is, I say if I give A0, but how can I choose A0? In the one-dimensional case, we know arbitrary. And now, let us see why. Is A0 arbitrary? You can ask. No. And this will come from the third type 2 commutation relation. In fact, the type 2 commutation relation gives this lemma. No, type, the number 3 of type 2, not the number 2. Number 3 of type 2, commutation relation. Number 3 is equivalent to I have put the proof in the lecture, but they are algebraic, they are not difficult, they are simple. Some is rather long, but not difficult. So I want to explain the idea, which is more important. So, this is equivalent to the fact that to understand again this relation, let us understand why this helps us in the reconstruction. Because if you restrict to n, as we did there, you start from n, a daga, k, and you start from a vector in n. Then you arrive to a vector in n plus 1. So this AJZ will be the one on n plus 1. And this will be minus the same thing, because they are both on the left. This you will have A0k on n plus 1 times a daga j on n. This will be, I start now from A0, which is gradation preserving. So this is A0 restricted on n, and since A0 is gradation preserving, this will be again restricted on n, not n plus 1. You see, that's the crucial point. So you interpret this. Now they are matrices, because when we take AJ and we restrict on the n space, we have a matrix, because this Pn is finite dimensional. So you have a matrix, and so you have an inductive relation that if I know A0n restricted to n, let us call the n component of A0, and the n component of the A daga k, then by solving this equation, because Kn is known, I suppose I know this matrix, okay? And then I recover A0 n plus 1.
Knowing at the end stage gives you
as you see, is a linear equation. This is a linear equation. So one open problem that I would like, if there are I'm sure that an expert of linear algebra should be able to say exactly, if I give you this, and I give you this known matrix, this is a known matrix. How many parameters? It's clear that it's clear. I mean, I think that one could prove easily that the solution of this equation is not unique. Probably there are many solutions, but I have not a proof of this fact. So, suppose that there are many. Suppose that there are many. Which is the exact number of parameters that labels this? That will give us the analog of the alpha n, because the alpha n is the minimum number of unknown parameters. Of course, I could say these are this A0 n plus 1 is a matrix in a space of dimension dn plus 1. Remember, dn goes like n to the power d minus 1. Okay? So, of course, I have this is the number of parameters is less or equal than dn plus 1 square. But how much less? If we have this, we have a full parametrization of probability. At least we should do another. Well, in order to have full, we have also to discuss the ambiguity in omega tilde. But you see, because of the first lemma, the imaginary part is fixed. Fortunately, the imaginary part is a skew-symmetrical. So this doesn't, the fact that the imaginary part is fixed does not put any constraint on the real part. I can choose arbitrarily the real part. And I will always have a positive definite kernel, so a scalar product. You see? That is the important part. However, this shows that, for example, in some cases, it is impossible to choose the kernels so that they are skew-symmetric,